which is fun. It's really just a bunch of case histories, but they're pretty informative. And I made a few examples to do some of these. So this is not where you've got a simple signature like the apostrophes coming with SQL injection or some defined code. So it's kind of hard to imagine any kind of automated scanner picking up these errors. These are errors in thought, where you just did not think about how step 1, step 2, and step 3 lead to some undesired consequence. And therefore they happen all the time, especially when you have a big sprawling app written by different people in different languages on different systems who made assumptions that were not clearly stated about what input was coming in. And so you'll see a lot of these happening. So here's some examples. This one here is asking the Oracle. You may remember in a previous chapter we did some encryption attacks where you attack encrypted code without decrypting it by just scrambling it around. And this is more of the same trick. Defeating the encryption itself is hard. That's the point. If people use anything like a modern algorithm, you're never going to find a hole in the algorithm. So you just have to find some other mistake they made that makes defeating the encryption unnecessary. This one here, he's got a remember me function. Now, remember me function has to put a cookie on your machine that has some long, supposedly random string. And they have to construct it somehow. And if you can reverse engineer how it's constructed, then you could forge somebody else's remember me cookie. So it's supposed to be something hard. So what this one did was take the name and user ID and some kind of volatile data like a time or something, and then put in the IP address and then store it locally so that if someone copies the cookie to another IP address, it won't work, which is a good idea. But the screen name is also stored in a separate variable called screen name. And they chose to encrypt that, which was probably kind of unwise because the screen name is not a secret. But since they did choose to encrypt it, they used the same encryption module to encrypt it, because once you got one, you would reuse it, of course. Now the problem is the user can control the screen name. So I can pump in text and it will encrypt it for me. And I create encrypted text of anything I want with their encryption module. And so I can't decrypt it, but I might not have to, because what happens is my cookie that records my name is encrypted and it decrypts it and prints that name on the screen. So now I have an arbitrary encryptor and an arbitrary decryptor I can call, thanks to this function. So you copy the remember me cookie into the screen name cookie and look on the screen and you'll see the decrypted thing. So now you see it structured Marcus 734, one IP address, then some number. So change the name to admin instead of Marcus. And then use the cookie encryptor to encrypt it. Log out, log back in, now copy the screen name cookie to the remember me cookie, and now you're the admin. So they gave you a handy encryptor and decryptor module you could use. And this is the problem. And the fundamental error here is they have taken a high privilege important task and a stupid unimportant task and done them both with the same module. And we're going to see this happen quite a few times. And you can see how everybody thinks they're doing something fine. The person putting up the screen name thinks they've done a fine job. They've even protected your privacy in some foolish way. The encryption person thinks they've done it. You know, it's only someone that can look at the big picture would be it. And you have to have a certain kind of mind to look for these holes. So here's the steps. Look for things that are encrypted, not hashed. Things that are hashed are much less useful because it's not reversible, not easily. And then look for anything where you can control the data, and that data gets encrypted. And then you can try flipping the encrypted values around and see if you can cause an error that reveals the decrypted value. Anyway, so then there's a password change function. This is really common. Of course, you go to password change, it asks you for your username, the old password, the new password, and confirm the new password. And then you can get in. However, there must also be an administrator page, which can do this without knowing the old password. It has to exist. And these guys decided to use the same code for the administrator page, which is also reasonable. The problem is there has to be some way for that code to know if you're the administrator. And what they did was they decided that if it comes in without an existing password, that means you're the administrator, because the administrator form doesn't have that field. So all you have to do is remove that parameter from the request that comes from the other field, and you're the administrator. So,
Can you go back to that?
what's that?
Can you go back to
Yeah, I'm going to demonstrate it.
that? Oh.
That might help. Now I set that up here. I set up a bunch of these here. All right, and so here's this one. So I'm logged in as Wally. Old password, new password. I can submit, and I've got a password reset approved for Wally. But I want to be the administrator, so I have to change my name to the admin. And then when I try to change Wally's the admin password, it's going to say I'm denied. Because, and you can see the request up here. And the trick is, now if I just don't fill in the old password field, that's not going to do it. I'm still denied because I'm not the administrator. In order to be the administrator, I have to not have the old password parameter on the form, which the developer figures means I'm coming from the administrator form. The administrator form sends only that data. And now I'm the administrator. And so, I mean, there should have been something else, proving you're an administrator like a real cookie or something, but this is what tends to happen. And I think it's kind of funny because I'm too lazy to actually do things right. And I'm always doing the stuff that he talks about in his book, like too lazy to really write a whole bunch of code. I'm trying to make a demonstration for one little thing. So I'm always storing everything in temp files, creating race conditions, and storing things that are not really in sessions. Like it's just stored in the temp file. It's the same for everybody. If 10 students are doing the project, there's one file getting overwritten over and over. All these, I can see how this happens because it's exactly the same as these developers. I can't really be bothered to properly set up a database and a bunch of code and all that jazz. And neither can they. Especially when they're just trying to add something in a hurry. So anyway, all right, so that's the problem there. So try removing parameters completely and see what happens when some parameters are missing. The parameter pollutions, we have the same parameter in there twice. You could try having it in there not even once and see what it does. Now here's another one. So you browse the catalog, you add items to the shopping basket, then you go to the shopping basket, approve the order, then you enter payment information, then you enter delivery information. But the developer, of course, assumes that these things are going to happen in sequence. So if it's time to enter delivery information, you must have actually finished the payment information. So all you have to do is proceed directly from step 2 to step 4. And if you can enter step 4, it assumes you've taken care of the payment information and you set up delivery information and get the product without paying for it. So again, this is the thing, if there's a series of steps, try skipping steps, doing them backwards, find the URLs, guess their assumptions and violate them. You know, that's the game. And this is why it takes a human, and a robot's not much good at it. You have to sort of think about what they expect to happen and think about how to pervert it. So here's one. Okay, this one here, these are obvious commercial buttons. It's kind of obvious which companies he did too. Anyway, so these are online purveyors of insurance. And you go there to get a quote. And remember, these guys will send you, put ads saying, our insurance will be cheaper than the other guy. So go to our page and you can get a quote and we'll find out how much money you'll save. So that's the point. So the first thing, you fill in basic information, you know, how much money do you make, how much is your car worth, and all this jazz. And then the app computes. You give it financial information, and whatever you didn't give it, it computes the other missing values to try to help you along. Then you go fill page after page with all these details, then it's going to give you a quote for life insurance and car insurance and everything. And you make an application which is then sent to an underwriter. Now the underwriter will look at this and try to make a judgment. So there's a human in the loop. So they try to notice if you have, if the stuff is obviously lies or inconsistent, or if there's some zinger in there, like you have previous convictions for wrecking your car or an alcoholic or something, then they would like to modify the quote. So the underwriter does that on the same web app. They view the code on the web app and they just change flags on the same data structure to record that they've now analyzed it and approved it. So there's a shared component to process each parameter, and it does everything in post requests. And the plan here is that each request will contain only parameters requested in the current form, just like the last one. They don't consider that things might be changing. So the point is, supply validate at the early stage, then you override it with later requests, changing the same value. And this allowed cross-site scripting injection, because they did not, if you put in data for step 1 in step 9, they didn't revalidate in step 9, so you could take the data that was there. It's just like when you put up an ad that's innocent, then after it's being displayed, you change the code to malware, and it will take them a while to catch on. So you can also purchase insurance at an arbitrary price, because you can force approval, because when the underwriter sets the parameters, they then go on to a later request, and you can just replace the underwriter saying no with the underwriter said yes, and move forward. That's the kind of thing that tends to happen. So, take parameters from one stage, put them in another stage, see if they are tested for consistency. This is a fundamental issue we talked about in previous classes. Instead of storing everything on the server where you actually put things in the browser, which then come back. Here, there is data in the server, but the code is probably sloppily written, so it just takes every parameter that comes in and rewrites the data on the server. So you rewrite it for one value, then later on you rewrite it for another value, and now I'm not going to be checking it anymore because I don't expect to be rewriting it at that stage. So here's another one, just like every bank. So they have this online banking. They want you to do the online banking. They'll send you the form, try to get you to do it. So it collects your name, address, and date of birth to try to make sure that you're really you and not someone else breaking into your account. Then it sends a request to the back-end system, and then it mails a pack to the customer containing instructions and a phone number to call and a one-time password to start your online banking. This is how my banks all work. Okay, they regarded this as safe. Some personal data is required to start the attack, so it shouldn't be possible for an unknown person to do it. The one-time password is sent by mail, not on the computer, and the customer has to call in and authenticate from information like part of a PIN or something, so they have some verification everywhere, and it's stored in a database. There's an object like this, first name, last name, database, all this jazz. Okay, so that was their original system, and that was fine. But the problem is this same data object is used by two processes, one high privilege and one low privilege. The first this is the same data object that is used for real online banking once you're in. It persists forever. So the registration process changes the content of the same thing that's used for real online banking. And therefore, the account details are generated from the customer number, and the main banking application has like two-factor authentication and everything, but the registration process has only this weak identity proofing because the new customer can't have the password and the token and everything. So you log in with valid credentials, and once you have an authenticated session, go to the registration function and submit a different customer's information. This will overwrite your customer object with the new object pointing to the other customer. And now you're the other customer you get in their bank account. Because the registration process is not secure, and the banking process is secure, they both go to the same data store. It's again, a subtle logic flaw.
How do you get their personal information?
You will have to get some personal information, but it's very simple. You just need to get their birthday. So you just go to Facebook or something. Yeah, you have to do that much at least. And that's what everyone's found. That's why everyone gets in Gmail and everybody's email, because the password reset for your birthday or last 4 digits of your social is information that is pretty easy to get. And if you can't get it, you can just brute force it. So anyway, that's the point. The fundamental flaw here is that the same database object we've written two ways. The main banking function after strict authentication and the registration function after not much authentication at all, both going to the same thing. So here's another one, extremely simple. You have a financial transaction company, you have bank, you're allowed to transfer, this is how the guy that stole 5 billion euros in Britain did it, in France did it. He was only supposed to be able to invest like 100 grand, but he invested like billions of dollars and lost them, and immediately got hired by another person for being a genius. So he overcame their internal transaction limit. So here you got a transaction limit where you can only make transactions up to $10,000. Anything above that has to have a manager's approval. And the code looks like this. If amount less than $10,000, go ahead, otherwise return true, this one has to go to the management. Okay, that's fine, except all you have to do is put in a negative amount. The negative amount is always less than the threshold, and the bank apps will accept it and just move the money the other way. So I'll just pay my bill of minus $1 million today. I paid it on time, and I think I'll leave now. So that's it works. This tends to work in a lot of these things. So that's very simple. I thought they were going to do the slightly more sophisticated one, where you roll around the numbers. You know, computer numbers only go so high, and then they roll around. So if you could only have like 100 characters, then you have to put in like 16 million characters, so it appears to be minus 16 million, and that's less than 100. But anyway, this one's even simpler. Just a negative amount. Yeah.
Is there any real case when this actually worked in the past?
All these are real. These are all real case histories of people that paid the author to do pen tests. Oh, there are tons of these things that have happened. I mean, you can never imagine that something is too stupid to happen. Everything will happen. Because there was an innocent age, like the 90s, when nobody understood any of this stuff. And they all started putting all the business on the web, and they didn't know anything about anything. And there's still a bunch of developers from that innocent time. Yeah, well, you know, this is what happens. There's no real training, there's no certificate, there's no license, there's no inspection. You know, everybody can just put up a store on the web, and so a considerable number of them just don't know what they're doing. Yeah.
Well, a lot of it is like some code used to be internal, but then everyone wants to be open data, web interfaces, this, that, the other. So stuff that was never coded to be outside of firewalls suddenly is exposed. That's true. And Microsoft encourages that. Microsoft's designed to help you do that. So, I mean, and also you use code base they get from other people and code that was written by previous generations of people and just stuff they download off the internet. You know, it's if you think about how it's done, it's not surprising that everything, no matter how stupid, is happening.
What about the situation now? Are companies and organizations much better?
I think banks are a lot better than they used to be. I think banks have gotten hacked so much that most of them now do like a certain minimum level, like PCI compliance sort of stuff. In my experience, most of the security at banks don't really understand anything, but they do try to make sure that they're not doing anything worse than the other guy. So if they only know the simplest things, and anything complicated, they just try to see, is this the industry standard practice? Well, then shut up. But they're thinking about liability, then that's not entirely stupid. I mean, you can't sue them if they're doing as much as the other banks do. That's why banks didn't use HTTPS until about 6 years ago. They just lied. There was a formal statement you could get on every bank page why this is secure, that they have an HTTPS button on an HTTP page. They got somebody to write a lie, and they all put the same lie on their pages. And I complained to them, my banks I was in, I escalated as high as I could. They promised to get back to me, never get back to me. It was just a bald-faced lie. Now, somebody told me that there was a law change about 6 years ago. They actually made them liable for this, so that's why they switched to using HTTPS. But, this is not because they're evil, it's because they're in the business of making money. So it is their job to put the minimum effort in to make the most money. If they did something else, they would not have the maximum return on their stock. Anyway, but that's the way it is. And so some traditions are coming up, but a lot of businesses, like especially government, especially non-military government, it's just way, way back in the dark ages. So here's numeric limits. So retailing application, there's a bunch of these things. You can't order more than in a stock. You can't make bill payments that exceed your balance. An insurance application may adjust its quotes on age thresholds. So putting in negative numbers and all these things might be fun. Maybe if the older you are, the more life insurance costs. Maybe if you're minus 100, it's free, or they pay you money or something. So then you can cheat on the bulk discounts. There's a ton of these, man. I remember I went to Microsoft and tried to get like 5 free thumb drives a few years ago because you could just change the parameter. So these guys have a discount. If you buy one product, you pay full price, but if you buy like their whole pile of products, antivirus, firewall, and anti-spam all together, you get 25% off. So all you have to do is put them all in the basket and then take most of them out and buy, and the discount remains. So this is the kind of thing where they just didn't think it through. They didn't remove the discount on removal from the basket. They just added the discount upon adding to the basket. This reminds me of, I think it was Home Depot, or it was either Safeway or Home Depot. I think it was Safeway. The first automatic checkout machines. I went there and they had like a refund button, and it would pop up on the screen, "Don't press the refund button." And if you did, until after this screen, and if you pressed it at that screen, it would give you a refund and give you the product. It was bloody awesome. Anyway, and that was their workaround, was to put a message on the screen, "Now don't press the refund button." And they just don't think about the kind of people where that's going to make me press the button. Anyway, so, and then there's this one's cute, escaping from escaping. I got this one set up. So the developer has a intrusion detection system, web interface. This is a real one. Again, these are all real. And they have some kind of form which they implement by executing command line code. So it's like a ping form. And they know that there's a risk of command injection. So to prevent the command injection, they add a backslash to escape out all these characters which could be used to run 2 commands on a string. So that sounds pretty good, so let's try it. That should be one of these things here, the logic flaw demos, yeah. All right, so yeah, here we are. Here's the ping form, google.com, you can ping google.com. Okay, so there it goes pinging. But now if I try the usual stuff like ls, it doesn't work because it puts a backslash before the semicolon, so it's not interpreted as a meta character, and it's just an invalid command that won't execute, which is not harmful. Now, and you can try a variety of them, so if I can try various other things that might work here, like pipe, and the pipe is also backslashed, but the error is that the backslash is not backslashed. They did not think of that. So if you put a backslash, semicolon ls, then the semicolon will be backslashed, and the backslash will not be backslashed. So the result is it backslashes the backslash, causing it not to be a meta character, so it does not override the semicolon, and now you get the ls. So this is one of the many examples of the failure of blacklisting. If you try to enumerate all the bad things, this is just a challenge to the ingenuity of the attacker to find some screwy way to do it that you didn't think of. It would be better, if they just let through letters and no numbers or something. But anyway, that's the game there. So that's the failure of, they call it escaping. You escape it, but you forgot to escape enough stuff. All right. Then there is input validation. So this one is pretty cute. You have SQL injection, and you're trying to prevent it. So you want to remove the apostrophes. Now, as we talked about, you could just remove them, but that would be rude. What's the best thing to do is make them double apostrophes, because then they stand for apostrophes, and you can actually have names with apostrophes in your database, and it will work. So if you put in admin apostrophe dash dash, it will turn that into admin apostrophe dash dash. So this is treated as an apostrophe, and now you will look for the literal name admin apostrophe dash dash, which is what should happen. It's not a meta character, it's a name. Names can now have dashes and apostrophes in it, which is certainly the way it should be, because real people's names do have apostrophes and dashes in them, and you shouldn't be removing them just because you're not a very competent programmer. So, however, the problem is they also put in a length limit. So it did two things. First, it escaped the quotes, and then it truncated to 128 characters. Now, by the way, this is a bad idea. If you're going to have a length limit, the right thing to do is, if it's longer than the length, reject it and make them type it in again. But it just truncates it at 128. So, of course, you can see what's coming. You put in 127 A's, followed by an apostrophe. It adds another one, making it 129 characters long, and then it cuts off the apostrophe from the length limit. And now you snuck in a single apostrophe. So now you created a SQL syntax error by having 127 A's and an apostrophe. So, you know, your one sanitization has undone the benefit of the other one, which tends to happen a lot. And so now the attack is, you submit the same username and a password of this, and now you end up with this weird thing, and I colored it in red to try to make it more readable. The username equals, quote, this mess, that's interpreted as the normal quote, and password equals, it's all part of the name. This is the end of the quote, and now it's or 1 equals 1. So it has the usual effect of always being true and giving you the whole database, but it's a little hard to read. And you've had to use two parameters together to create the desired goal instead of being able to put it in just one field. But you can still get there. So if you want to detect this, here's some things to try. Have a series of apostrophes with a quote, and then put a letter in there in a quote, and see if you can manage to create the SQL syntax error, because that's what you're looking for. When you see the syntax error, then you know that it's just a matter of formatting things correctly, and you'll be able to do whatever you like. All right, then there's a search function. So these guys had it. This sounds like LexisNexis. It's kind of fun to guess which company he's talking about. But anyway, so they have a huge archive of information, but you can't get there unless you pay. However, to promote it, you can do searches against it without paying, and it will tell you how many hits there are, in like one line out of each page, to tantalize you. You could be seeing all this great stuff if you paid, which I'm pretty sure that is exactly how LexisNexis works. So the idea here is that you can't get anything useful from the search function without paying. And the document titles look like this. They're kind of cryptic and such. So here's the attack. You have to guess at the content like blind SQL injection, and then the number of hits will tell you whether that phrase is there. And you can search for a literal phrase. This is like the project you guys are doing where you're trying to find a numerical file name by guessing until you see a change. So he tries a press release merger and finds 0, so then he tries share issue and finds 0, then he finally gets a match with takeover. So you just try words until you get a hit. Then you know that word is in there. Then you know this word is in there. You can gradually get the gist of this press release by a dictionary attack, essentially. This is the same as that blind SQL injection that we did. And so you can also brute force a word if you're serious about it. You can brute force one by letter, and that's what you're doing in that project where you're trying to find a long file name. By the way, somebody actually turned it out. I was grading it today, and somebody actually did 1,000 queries to get the 3-digit one, and strangely, they did not do the 9-digit one. Like I say, I mentioned in class last time, this is not the way to do it. You can do one character at a time. So the 9-digit one will either take 1 billion guesses, or it will take 90 guesses. There are two algorithms. I highly encourage you to do one character at a time. Yeah. But that's why I did it that way, because you can do the 1,000 the hard way, but you can't do the billion the hard way. Anyway, all right. And then there's debug messages. The error messages are always a rich trove. So these guys have a new buggy app. So the error message right now puts out all kinds of stuff. Now the parameters, the tokens and everything. But the point is, that's not a security flaw, because the user could see all that by just using Wireshark or something, see what's coming out of their browser. It's just their session that appears on their screen. This way, when they call to the help desk, they can like take a screenshot or read these numbers to the help desk person. So it's just to fix the app, see? But the problem is it did not get that data from the browser. It got that data from the server, which is not exactly the same thing. And on top of that, and just like what I would do, when this is a temporary error condition, they're copying all of it to one server object, the latest error message, which is not tied to a session, and then displaying it on the screen. So what this means is, if two people log in at the same time and have an error at the same time, the container gets overwritten by somebody else's data, and then it appears on your screen. You see somebody else's cookie and such. You created a race condition by having a shared object that is not tied to the session on the server. And of course, this was just a temporary thing while we have the bug to work the bugs out. But anyway, that's the game here. And this is so in the first place, there's a race condition, and there's a temporary window of vulnerability. But this is even worse than a race condition. All you have to do is write a script to pull that object continuously. And as people log in and out, you'll get everybody's tokens. Every time they log in, their token goes in there in case they have an error, and you just get them all. So you have taken a privileged object that should have been in an authenticated session and put it in a container that's available to everyone. And that's obviously bad. So here's a similar one racing against the login. So these guys have a robust login process which has been pen tested and subject to design reviews, and everybody has great confidence in it. But the problem is they notice that sometimes people see another person's account. And by the way, this is quite common. It happened to me. It happened to a student in big services like Verizon and stuff. You go online, you get in somebody else's account, people are sending around screenshots. This really happens to big companies, and if it only happens like once, a couple times a month, nobody can ever figure out what it is. These bugs just persist. But anyway, so they eventually found out that when two users log in at precisely the same time, this happens rarely, not even predictably then. And so what they found is the same mistake. A key identifier like the session ID was not really stored in a data object tied to the session. It was stored in a static non-session variable. So people were overriding it, and it was read back an instant later, but there was a brief period of time when someone else could override it, and then when you read it back, you'll be in the other person's account. And this is how all my pages are coded, because I'm too sleazy to set up a database. So I just read something, put it in a temp variable, and I read it back later, and I know it's a phone, but I don't care because I'm deliberately writing bad stuff. But it's a whole lot easier to write bad stuff than to just rigorously set up a stinking database and sessions for everything when I'm just, trying to make something for people to hack into. It's too much bother. Anyway, so that's the point. If a different thread comes in and changes that variable, then you'll see something else. So if you want to avoid this stuff, what you have to do is you have to rigorously document your code. You have to actually write a module, and then you have to document what exactly is the data coming into this and what assumptions have I made about that data. And what exactly is the data going out and what assumptions have I made? And then people say, they can only come in here if they're an authenticated user with a current session, don't take something else and use this module for it. Yeah.
Or don't write your own login authentications, like use the libraries in your language.
Well, that might help as long as you really read the documentations and you really understand what assumptions libraries are making. Mm-hmm. Yeah, that's right. Anyway, so you document everything, the purpose, the assumptions you make, and you also document all the other things that are using this in your code, so you know what modules are using this, and therefore you have some chance of noticing that one of those modules is dangerous and anybody available to the whole world. So during security review, you consider all these things, imagine circumstances to violate the assumptions. That's the idea. This should be an S. All right. Anyway, and obviously the high priority things to fix are things that the user can control. Now, so that's it for this one. I've got some cross-site scripting to talk about. Let's take a break till 10 after 7, and I'll carry on to that. We'll do the first part of the cross-site scripting class. This is chapter 11.